Hello and welcome to this video on memory and revisiting the idea of execution of instructions by the CPU. So in the last video we finished up with a diagram something like this. And the idea was that our model of execution was that we go through each of these instructions on the left, they get fed to the control unit which then initiates the appropriate actions to execute these instructions which make up our program. But this may raise the question of, well, how are these binary digits actually going to get to the control unit? And actually, where are these binary digits even stored? Well, in the bigger picture, the CPU does not exist in isolation. A modern computer may well have multiple CPUs to start with, though in the first part of this course we're mostly going to be talking about uniprocessor architectures, that's computer architectures with a single CPU. But aside from that, your computer probably also has some form of memory, that is some way of storing binary digits, bits of data, and your computer probably has some other things attached to it too, like I/O devices, input-output devices such as your keyboard or a monitor. If you don't have some form of output in your computer, good luck trying to see the results of the computations it does. In most computers, all these pieces, so the CPUs, the memory, all the I/O devices and all the other stuff, is connected through communication channels called buses. You might want to take a look at buses in your own time, particularly the details of buses on any particular architecture that you're working with and trying to optimize on. But let's zoom back in from this bigger picture and let's take a look at memory this time. So as I've alluded to, memory is essentially just a way to store binary digits, to store bits. Typically when we're talking about the main memory of a computer, we're talking about some kind of storage size which is greater than that in registers, but as a result is slower to access than registers. So the fast computations inside your CPU are still going to be using registers for their computation, but usually we store data for the longer term in this main memory. And just like we can encode instructions in different sequences of binary digits, we can actually encode lots of different types of data, such as numbers and text and so on. These can all be boiled down through encodings to binary digits. Typically in memory, we create groups of binary digits, groups of bits, which we call bytes. Most modern architectures deal with bytes that are 8 bits in length, but you can have other architectures with other byte sizes. And then once we've split the bits up into these groups, into these bytes, we can then number each byte in memory, so we can talk about a particular byte in memory by its number. One of the reasons splitting all these individual bits up into bytes is useful is because it makes it manageable to number these different locations in memory. We can number every group of 8 bits, for example, instead of having to number every single bit. So let's just populate our memory with some data here. We could talk about this byte as being the 0th byte, because we usually number the bytes from 0. We can then talk about this byte as the 9th byte, because if you count from the beginning, we have the 0th byte, then the 1st byte, then the 2nd byte, and so on, and this is the 9th byte. So we're counting everything in one row here before we go to the next row. We can then talk about this particular byte in memory, this particular group of 8 bits in memory in this case, as the 54th byte in memory, and so on. This number that refers to a particular byte in memory is called the memory address of that byte. So we can refer to a particular byte in memory, a particular series of binary digits, by the address of that byte. So to make it a little easier to look at the memory address of each byte here, I'm just going to label each row in this diagram with the memory address of the first byte in that row. So our first row in this diagram goes from memory address 0 to memory address 7, our second row goes from memory address 8 to memory address 15, and so on. It's typical when we denote memory addresses, however, to use hexadecimal. This is just a number system with base 16, so if we're counting in hexadecimal we go 1, 2, 3, okay that skips some, so we go 8, 9, but instead of going from the number 9 to the number 10 to the number 10, we use the letter A to denote 10. We then use B to denote 11, C to denote 12, and then after F we wrap around, so we go to 10. So 10 in hexadecimal is not 10, it's 16. And then again the same kind of thing happens, so we might go 18, 19, 1A, and so on. So let's just change our memory address row labels here to use hexadecimal, and we typically denote this with the OX prefix. An important property of memory in modern computer architectures is that it's usually a specific type of memory called RAM. RAM stands for Random Access Memory, and essentially what this means is you can access any byte, so the byte at any memory address within our memory, and it's going to take the same amount of time as accessing any other byte in memory. We could read all 4 of these bytes here and it would take roughly the same amount of time because the memory is random access. And this really matters because if it took a significantly different time to access bytes at different locations, we'd have to take this into account when designing algorithms. Now let's actually just focus on this particular byte here, the set of 8 bits with the memory address OX41 in our diagram. What does this set of binary digits 01000001 actually mean? This might sound like a kind of philosophical question, and, well, it really is, because we can't say without context what this particular series of binary digits means. It could mean literally anything depending on how it's interpreted. So this set of binary digits could represent the number 65, Or it could be in some crazy encoding and actually represent the number 190. Or maybe this is actually supposed to represent a textual character. So maybe it represents the uppercase character A in some particular text encoding. Or maybe actually the set of binary digits is supposed to be an instruction that the CPU reads. Maybe it's an instruction to add the following two operands that are in the next few bytes in memory. The point is that data is just data and it is nothing else, and without context, data cannot mean anything. So with this newfound knowledge of memory, let's revisit our execution model, this time with RAM in the picture. Our diagram of an imaginary processor here, while good for explanation purposes, probably isn't entirely accurate as to how you might actually design a CPU to be in the flesh. For one thing, the different sections of the processor probably wouldn't be as segmented as the diagram make them look here. Most processors have some registers within the control unit, some storage within the CPU that helps manage the operation of the CPU. Most processors have something like the register we're about to describe called the program counter within the control unit. On the x86 family of processors, for example, this register is called the instruction pointer. And what it does, in general, is keep track of the next instruction to execute. Because execution typically goes sequentially through memory, we might execute an instruction and then increase the value of the program counter so that it points to the next instruction that we need to fetch and execute. Generally, this whole process makes up something that we call the fetch, decode, execute cycle, the FDE cycle. And while this process is somewhat complex on modern processors, we're going to walk through a simplified FDE cycle right now. So first off, our program counter starts with the value 0, which refers to the memory address 0 in memory, and so our control unit reads our first instruction from this memory address. Typically it's going to do this through communication channels known as buses, which I alluded to earlier, and usually memory requests from the CPU actually go through a unit called the MMU, the memory management unit. But we'll talk about that in future, we're not actually going to discuss the MMU right now. So the control unit fetches the binary digits for this particular instruction. Typically it does this through some other registers internal to the control unit. And in this example, because our instructions span multiple bytes, it may actually fetch the first byte first and then figure out it has to go back and fetch our second byte. After this fetching of data, the control unit has to decode the instruction, and there should be some circuitry within the control unit to do this. After the instruction has been decoded, it can then be executed. So the control unit can send the appropriate signals either internal to the CPU or over buses to other sections of the computer to initiate the action that the instruction requested. After the instruction has been executed, we can then increase the value of the program counter as appropriate to point to the next instruction. In this case, because we just executed a 2-byte instruction and we started at the memory address 0, our next instruction is going to be located at the memory address 2. And then we can just repeat this whole process so the control unit can fetch and then decode this instruction and then send off the appropriate actions to execute this instruction, and then increase the value of the program counter as appropriate to point to the next instruction so that we get our sequential execution. And this process can continue until we've finished. If you're on a modern computer architecture, the chances are that every single program executing on your computer will have to go through a process something like this on the CPU level. An instruction will be read from RAM, it will be decoded, and then it will be executed. And then the value of the program counter will be adjusted as appropriate to the memory address of the next instruction to be executed. And by the way, because we're storing all of our instructions in RAM, which we're doing by the way because programs are typically too big to fit in registers, that if our program consists of less instructions, that it's going to take less space in RAM. And so if you're optimizing for memory usage, using less instructions is one way to go about that. So that's really all I had to say in this video. We've discussed memory, we've discussed bits and bytes and data, and we've discussed the fundamental topic of the fetch, decode, execute cycle, which is used to execute programs on modern machines. So that is all for this video. I will catch you next time.